Welcome to the deep dive. Today we're tackling a really fascinating challenge right at the heart of cutting-edge AI.
hmm
How do you actually use these enormous large language models efficiently, without needing a giant server farm running flat out?
Yeah, think about something like Llama 3.1 405B. Incredible model, incredibly powerful.
But huge.
Exactly. That's right. These state-of-the-art models, they need immense resources. A model that size in the standard bfloat 16 format needs something like 810 gigabytes of memory just to operate.
Wow. 810 gigs.
Yeah, and that often means you need these really complex, really expensive multi-GPU setups. It's a big barrier for a lot of people.
It really is. The size itself makes getting access a major hurdle. But today we're going to dive into some academic research that offers a potential breakthrough. It's a new method called defloat 11.
Right.
And the promise here is pretty remarkable, shrinking these massive models down by about 30%, but, and this is the key bit, without losing any of their original accuracy. So genuinely lossless compression.
And what's really interesting about dfloat 11, I think, is its specific goal. It's not just about making the file smaller for storage, though it does that.
Okay,
The real innovation, the focus, is enabling these smaller models to run much, much more efficiently on, the kind of GPU hardware that's more readily available. It's about making top-tier AI a bit more accessible.
democratizing it in a way.
You could say that, yeah.
So our mission here is to really unpack defloat 11 for you. We want to dig into the core innovations, understand how this lossless compression actually works, and figure out why it could be such a big deal for LLMs, especially for running them efficiently on GPUs. We'll definitely be focusing on the novel technical ideas in the paper.
Sounds good.
So let's start there. These huge parameter counts, like in Llama 3.1 405B, they directly cause these massive memory needs, right?
Precisely. Like we said, around 810 gigabytes for that one model in bfloat 16, and that immediately creates a huge bottleneck.
Because most single GPUs just don't have that kind of memory.
Not even close. Even high-end server GPUs might top out at, say, 80 gigs. So you're forced into these complicated, costly multi-GPU setups, sometimes even multiple machines networked together.
Which adds engineering complexity,
A
cost.
lot of overhead, yeah. And it fundamentally limits who can actually train or even just run inference with these cutting-edge models.
And for you listening, if you're following this space, you know this resource problem is a major driver for innovation. It's not just about making models bigger anymore.
Right.
It's also about finding clever ways to make them usable, practical, within the hardware we actually have. And we have seen other ways to compress models, haven't we?
Oh, absolutely. The most common approach you hear about is lossy compression, and quantization is the big one there.
Quantization, reducing the number of bits per weight.
Exactly. Instead of the full 16 bits you get in bfloat 16, maybe you drop down to 8 bits or 4 bits, sometimes even less, and it definitely saves space, and it can speed things up too.
It's like rounding numbers more aggressively.
That's a decent analogy. You save space writing them, but you lose some of the fine detail. Some precision is lost.
But the key word there is lossy. There's a trade-off involved.
There has to be. The paper puts it quite clearly, actually. It says, quantization is inherently a lossy compression technique. It inevitably alters the output distribution of LLMs, thus impacting model accuracy and reliability.
So you're approximating. You're not getting the exact same model back.
Correct. You're changing the underlying values, and while it often works surprisingly well, it's not a perfect replica. You might lose subtle things the model learned.
Okay, so that's lossy. Then you have the traditional lossless compression methods, like zipping a file.
Right. Things like zip or Z standard, and they work great for making model files smaller when you need to store them or download them.
But
But as the research points out, existing lossless methods primarily focus on improving storage efficiency. Their advantages typically do not extend effectively to general purpose GPU-based LLM inference.
okay, so they shrink the file on disk, great for downloads, but they don't really help when you actually need to run the model calculations on the GPU itself.
Generally, no. You'd usually have to decompress the whole thing back to its original format before the GPU can work with it efficiently.
So DFlow 11 is aiming for something different here, a new angle.
Exactly. It's specifically designed to tackle that problem of running the compressed model efficiently on the GPU, and crucially, doing it without losing any performance compared to the original. That 100% accuracy claim is pretty bold.
It really is. So how do they achieve that? What's the core insight?
It comes down to a really sharp observation about how these LLMs store their weights, specifically in that bfloat 16 format we mentioned.
Okay, the 16 bits, sine, exponent, mantissa.
Right. 1 bit for the sign telling you positive or negative, 8 bits for the exponent, which determines the scale or magnitude of the number, and 7 bits for the mantissa, which gives you the precision.
Standard stuff. So where's the inefficiency they found?
The key insight is about that exponent part, those 8 bits. The researchers looked closely at the actual values these exponents take across many different large language models,
Man.
and they found that those 8 bits often contain way less actual information than you'd think based on the space they take up. They measured this using information theory, specifically Shannon entropy.
Entropy. Like how much randomness or surprise there is in the data.
Kind of, yeah. In this context, it measures the average amount of information carried by each exponent value, and they found the entropy of these bfloat 16 exponents was only about 2.6 bits.
Wait, 2.6 bits of actual information, but stored using 8 bits?
Exactly, that's the quote. The bfloat 16 exponents carry significantly less information than their allocated bit width, with an entropy of approximately 2.6 bits compared to the assigned 8 bits.
So less than a third of the bits are really doing unique work in defining the number scale. That's a lot of wasted space, information-wise.
A huge amount of redundancy, and that redundancy, that low entropy in the exponent, is precisely the opportunity dfloat 11 jumps on for lossless compression.
Okay, so how do they exploit that?
They use something called entropy coding, specifically Huffman coding. It's a classic, really elegant technique.
Huffman coding. I've heard of that. Isn't that used in things like JPEG or MP3?
It is, or variations of it. The basic idea is you analyze the frequency of symbols in your data, in this case, the different exponent values,
Okay.
and you assign shorter binary codes to the really common exponent values and longer binary codes to the ones that appear less often.
Ah, so the common stuff takes up less space. Makes sense.
Exactly, and because it's just a different way to represent the exact same values, it's completely lossless. You can always decode it back perfectly.
And what about the sign and the mantissa bits?
They found those parts have much higher entropy, much less redundancy. So dfloat 11 leaves them alone. It keeps the original sign and mantissa bits exactly as they are.
Got it. So the compressed model basically has two parts. This cleverly encoded exponent data.
Right. They call that the encoded expo.
And then the original sign and mantissa bits just packed together.
Yep, the pack sigmantissa. There's a good diagram in their paper, figure 2, that shows this breakdown.
Okay, so now the model is smaller, takes up less memory or disk space. That's good. But we talked about this earlier. How do you actually use these compressed weights efficiently on a GPU during inference? Those variable length Huffman codes sound like a nightmare for parallel processing.
That is the absolute crux of the problem they had to solve next. You're spot on. GPUs thrive on regularity, on fixed width data they can process in massive parallel blocks. Trying to use variable length codes directly in those big matrix multiplications, highly inefficient.
So you have to decompress them back to bfloat 16 first.
You do. You need to decompress them on the fly right before they're used in the calculations. But as the paper warns, this decompression step itself can become a major performance bottleneck. It quotes, "During inference, losslessly compressed weight matrices must be decompressed on the fly, and this decompression step introduces a critical performance bottleneck."
So just having the compression scheme wasn't enough. They needed a super fast way to decompress it right there on the GPU.
Precisely. And this is where the other major innovations of dfloat 11 come in. They designed a custom GPU kernel specifically for this task, and it has 3 really clever components.
Okay, let's break those down. What's the first one?
The first is about how they handle the Huffman decoding itself using lookup tables, or LUTs. A standard way to decode Huffman codes fast is with a big table. You read a chunk of bits, look it up in the table, and get the original value.
Simple enough.
But if your Huffman codes can be long, that single lookup table can get enormous, potentially billions of entries, way too big to fit into the fastest memory on the GPU, the SRAM.
Right, SRAM, that super fast on-chip memory, much faster than the main GPU memory, the HBM.
Exactly. So trying to use a giant LUT stored in the slower HBM would defeat the purpose. Their clever trick was to break down this potentially huge single UT into 4 much smaller LUTs.
4 smaller ones. How does that help?
Each small LUT only handles decoding based on the next 8 bits of the encoded stream. So each table only needs 256 entries. All 4 tables combined take up just over a kilobyte.
Ah, tiny enough to easily fit into that fast SRAM.
Precisely. So now the decoding lookups are incredibly fast because they're happening in the speediest part of the GPU memory. It's a neat decomposition.
Very clever. Okay, that's the first innovation, compact LUTs in SWAM. What's the second key part of their GPU kernel?
The second part tackles a complexity of managing these variable length codes in parallel. Imagine you have thousands of GPU threads all working on different parts of the compressed data stream.
Yeah. How does each thread know exactly where its chunk of bits starts? And more importantly, when it decodes its variable length codes, How does it know where to write the resulting fixed-size bfloat16 values in the output memory so they all line up correctly without gaps or overlaps? Yeah, with variable lengths, that seems tricky. Thread A might produce 10 values, thread B might produce 12. Their output positions depend on each other.
Exactly. So they use a two-phase approach. In the first phase, each thread scans its assigned chunk of encoded bits. It figures out where the first valid Huffman code starts within its chunk. They use a small helper array called gaps to store these starting bit offsets quickly. Then it decodes its whole chunk, but only counts how many bfloat16 values it would produce. It doesn't actually write anything to the main output buffer yet.
Okay, so phase one is like a planning step. Count the outputs and find the starting points.
Sort of, yeah. Then there's a quick synchronization within each block of threads. Using those counts, they can very efficiently calculate the correct starting output address in the main GPU memory for each thread's results. They use another small helper array, block output poise, for this.
Got it.
Then comes phase two. Each thread goes back to its same chunk of encoded data. But this time, using the fast LUTs in SRAM and knowing exactly where its output needs to go, it performs the actual decoding and writes the dfloat16 values directly to the correct spot in the main memory. They also load the encoded exponents into SLAM during this phase to avoid rereading from slower memory.
That sounds like a really well thought out way to manage the parallel variable length decoding. Very efficient. Okay, and the third innovation.
The third one is about the granularity of the decompression. Think about a transformer model. It's made of layers, and layers have different weight matrices: query, key, value, feed-forward networks.
Right.
Some of these individual matrices might actually be relatively small. If you tried to decompress just one tiny matrix at a time, you might not give the massively parallel GPU enough work to do efficiently. You wouldn't saturate its compute units.
You'd have idle cores waiting around?
Potentially, yes. So dfloat11 takes a coarser-grained approach. Instead of decompressing matrix by matrix, it decompresses all the weight matrices needed for an entire transformer block in one go.
Ah, so it batches the decompression work across a whole block, like the attention mechanism and the feed-forward network together.
Exactly. This creates a much larger chunk of parallel work for the GPU, keeping all those cores busy. It improves the overall throughput and helps to hide the latency of the decompression process itself. It amortizes the cost over a bigger operation.
Makes sense. Better utilization of the hardware. Okay, so to recap the kernel innovations, compact LUTs in SRAM for speed, this clever two-phase process with helper variables to manage the parallel output, and decompressing at the level of a whole transformer block for efficiency.
That's the core of the GPU side solution, yes.
Right, now for the payoff. Did it actually work in practice? What did their experiments show?
Oh yeah, the results look really strong across a whole range of models, different sizes of llama, Q, Gemma. They consistently got around a 30% reduction in model size.
30%. That's substantial.
It really is. Table 2 in the paper lays it all out. It effectively brings the average number of bits needed per weight down from 16 to about 11 bits.
From bfloat16 down to dfloat11, essentially.
Hence the name, yeah.
And the crucial point, again, was it truly lossless? Did accuracy take any hit at all?
None whatsoever. They checked standard benchmarks like MMLU for language understanding, truthful QA for factual accuracy. Table 3 shows the scores. The dfloat11 compressed models performed exactly the same, 100% identical results to the original bfloat16 models.
No approximation, just perfect reconstruction.
Perfect reconstruction. They even did bit-level checks on the decompressed weights to be sure. Zero accuracy loss.
That's fantastic. Okay, identical intelligence in a smaller package. What about speed? How did running the dfloat11 model compare to, say, trying to run the big original model when you don't quite have enough GPU memory?
That's a key comparison. Often, if a model is too big, people resort to offloading parts of it to the much slower CPU memory.
Right, which usually kills performance.
Exactly. So they compared dfloat11 running fully on the GPU against that CPU offloading baseline. Figure 3 shows dfloat11 was way faster, anywhere from 1.85 times to almost 39 times faster inference, measured in tokens generated per second.
Wow, nearly 40x faster in some cases. That really shows the benefit of keeping everything on the GPU, even with that on-the-fly decompression.
It really does. The decompression kernel is fast enough that it's much better than hitting the CPU bottleneck.
And the memory savings itself, does that unlock other practical benefits besides just fitting the model?
Absolutely. One major benefit is handling longer sequences of text. When you process text, the model needs to store intermediate results, the attention keys and values, in something called the KV cache.
Right, and that cache grows with the length of the input sequence.
Precisely. Because DFloat 11 frees up GPU memory by shrinking the model weights, you have more space left over for that KV cache. Their results in Figure 4 show they could handle 5.3 to over 13 times longer context lengths before running out of memory.
13 times longer context. That's huge for dealing with long documents or, really extended conversations.
It opens up a lot of possibilities, yeah.
And the result that really jumped out at me was the Llama 3.1405B test case, that monster model.
That's the big validation, isn't it? As they show in Table 1, DFloat 11 allowed them to run that 810 gigabyte model entirely on a single server with 8 80 gigabyte GPUs.
A single server node, whereas the original BFlow 16 version wouldn't fit.
Correct. The original 810GD model would exceed the 640 GB total memory of that 8 GPU server. You'd need a multi-node setup, which is much more complex and expensive. DFloat 11 brings it back within reach of a single, albeit high-end machine.
That's a massive difference in hardware requirements, potentially huge cost savings and complexity reduction. Did they compare DFloat 11 to any other lossless compression libraries?
They did. They compared it against NVIDIA's NVComp library, which uses a different technique called asymmetric numeral systems, or ANS.
Okay, how did DFloat 11 stack up?
Figure 6 shows DFloat 11 came out ahead on both fronts. It achieved better compression, getting that 30% reduction versus about 22% for NVComp in their tests, and critically, its decompression was significantly faster, up to 15 times faster throughput on the GPU.
So better compression and faster decompression. That seems pretty definitive.
It suggests their approach, combining Husman coding, specifically targeting the exponent with that highly optimized custom kernel, is really effective for this particular task.
So it feels like DFloat 11 isn't just a way to do lossless compression for LLMs. It's a way that's deeply integrated with making it work efficiently on the hardware that matters most, the GPU.
That's exactly it. It's a really compelling example of co-designing the compression algorithm and the hardware implementation. It offers a real, practical path to using these incredibly powerful, but previously often inaccessible AI models without needing the absolute bleeding edge, most expensive hardware setups.
It tackles that GPU memory wall head on.
It does through the smart mix of identifying the information inefficiency in BFloat 16 exponents and then building a specialized, super fast decompression engine for the GPU. The innovation isn't just the compression, it's the whole integrated system.
Okay, so wrapping up our deep dive then, DFloat 11 looks like a genuinely innovative lossless compression technique, custom built for large language models. It delivers that significant 30% size reduction, but crucially with absolutely zero loss in accuracy. And the magic is really in how it enables efficient use on standard GPUs.
Thanks to that custom kernel, yeah. With the complex ATs, the two-phase processing, and the transformer block level decompression working together.
And for you listening, the takeaway is pretty exciting. This could mean wider access to more capable AI models. You might be able to run bigger, better models on less extreme hardware or handle much longer inputs, all without sacrificing the quality or reliability of the results.
It really lowers a major barrier.
It definitely makes you think, doesn't it? How will innovations like this, focusing on efficiency and accessibility, keep reshaping AI? As these giant models become easier for more people to actually run and experiment with, what new things become possible? What doors does it open for your own interests or work?
That's the really exciting question looking forward.
Absolutely. And for those who are technically inclined, the researchers have made their code available and even pre-compressed models using DFloat 11, so you can explore it yourself.
Which is fantastic for the community.
It really is. Well, thank you for joining us for this deep dive into DFloat 11 and lossless LLM compression. We hope you found this look at the innovation driving AI efficiency truly illuminating.